Welcome to this coding session. Today, we'll be tackling LeetCode problem number 483, titled Smallest Good Base. This problem challenges us to determine the smallest base k greater than 1 such that a given number n can be expressed as a sum of powers of k. Get ready to explore the intricacies of this fascinating mathematical problem, and let's dive in. The problem we're solving is called smallest good base. A good base for a number n is a base k such that the representation of n in base k consists entirely of ones. For example, if n equals 13 and k equals 3, the base 3 representation of 13 is 111, which is made up of all ones. The challenge here is to determine the smallest possible base k for a given number n that satisfies this condition. The input to the problem is a string n representing a positive integer, where n lies between 1 and 10 raised to the power of 18. The output is a string representing the smallest good base k, which must be an integer greater than or equal to 2. Let's consider an example to make this clearer. If the input is n equal to 13, the output is 3 because base 3 representation of 13 is 111, and there's no smaller base that satisfies the condition. For more clarity, let's walk through the example where n equals 13 again. When we convert 13 to base 3, the result is 111, which is made entirely of ones. However, if we try a smaller base like k equals 2, the base 2 representation of 13 is 1101, which doesn't meet the condition of all ones. Now, consider another example where n equals 4681. In this case, the smallest good base is 8 because the base 8 representation of 4681 is 11111, which is all ones. Smaller bases such as k equals 7 or k equals 6 do not satisfy the condition. These examples illustrate how the problem requires us to find the smallest base where the representation of n is made up entirely of ones. Let's look at an example with a much larger value of n. If n equals 1 followed by 18 zeros, which is 1 quintillion, the smallest good base k turns out to be 9999999999999999999. In this case, when we convert n to base k, the result is 11, which is all ones. If we try a smaller base, like k equals 99999999999999998, the representation is no longer all ones. This example highlights the importance of efficiently computing the smallest good base for very large values of n while staying within the constraints of time and space. Now, let's consider some constraints and edge cases. First, the input n is always a positive integer, and the smallest good base k must be at least 2. Additionally, the representation of n in base k must be of the form 111, 1, with at least 2 ones. For edge cases, if n equals 1, the smallest good base does not exist because n equals 1 cannot be represented with at least 2 ones. For very large values of n, the solution must be efficient to handle the upper limit of 10 to the power of 18. Lastly, when n is a prime number, the smallest good base is typically n1, because in this base, n can be represented as 11, satisfying the condition of a good base. To solve the problem of finding the smallest good base, our goal is to express the given number n as a sum of a geometric progression in base k. This means we need to find the smallest integer k greater than 1 such that n equals 1 plus k squared plus k caret m1, for some integer m equals 2. To approach this, we first considered a brute force method. The idea here is straightforward. We iterate over all possible values of k starting from 2 and check if it forms a valid geometric progression that sums to n. For each base k, we compute the series sum directly for increasing values of m and verify if it results in n. However, this approach is computationally expensive because we need to calculate powers and sums repeatedly for a large range of values, leading to exponential time complexity. While simple to understand, it becomes infeasible for larger numbers. To address these limitations, we also explored an optimized approach using binary search. By leveraging the geometric series formula, we can express the sum as k to the power of m1 / k1, which simplifies the computations. This method focuses on finding the smallest base k by iterating over possible lengths of the series m, and for each m, we use binary search to efficiently determine the value of k that satisfies the equation. A key insight here is that the maximum value of m is bounded by log 2, n, because the series grows exponentially with m, significantly reducing the search space. To put the optimized approach into practice, we iterate m from log 2, n, down to 2. For each candidate length m, we use binary search to find a valid base k within the range of possible values. This range is from 2 to n-1/m1, which comes from the fact that the base k must fit the geometric progression formula for a given m. If such a base is found, we return it as the smallest good base. This approach drastically improves efficiency compared to brute force because it eliminates unnecessary computations. Specifically, the time complexity reduces to approximately O log 2 n * log n, which makes it scalable even for very large values of n. While this method requires careful implementation, it leverages mathematical properties to narrow down the possibilities and uses binary search to quickly pinpoint the solution. Another alternative we looked into was deriving a direct mathematical formula for k. While this approach is theoretically interesting, it introduces significant challenges in practice due to precision issues when working with large numbers. Additionally, the complexity of implementation makes this method less reliable for edge cases. Therefore, it is not as practical as the optimized binary search strategy, which balances clarity and efficiency. The chosen strategy for solving this problem is the optimized approach using binary search because it offers the best balance between efficiency and practicality. The key insight that makes this approach work is recognizing that the length of the geometric series, m, is limited by log 2, n. This drastically reduces the potential search space, allowing us to focus only on meaningful candidates for m. Furthermore, binary search ensures that we efficiently identify the smallest base k for each possible series length. This avoids the computational overhead of the brute force approach, where every possible base and series combination is tested. Compared to direct mathematical formulas, the binary search approach is more robust and easier to implement, especially for large numbers where precision issues often arise. A key observation is that the formula, k to the power of m1/k1 equals n directly connects the base k and the length m of the series. Additionally, the exponential growth of k(m1) means that m is naturally bounded, giving us a clear upper limit for our iterations. Overall, while the brute force method is too slow for large inputs and direct formulas are less practical, the optimized binary search approach strikes a balance by being efficient, scalable, and reliable. This makes it the most practical solution for determining the smallest good base. The problem we're tackling is to identify the smallest base, k greater than 1, such that a given number n can be expressed in the form of a sequence of all ones, 1 plus k squared and so on, up to k(m1), where m is at least 2. This means we're essentially representing n in base k, where every digit is 1. To solve this, we rely on the mathematical representation of a geometric series. Specifically, the sum of this series can be expressed as k to the power of m1 divided by k1. This formula allows us to directly check if a candidate base k and sequence length m satisfy the condition for n. Now, to determine the range of m, we note that the sequence must have at least 2 terms, so m starts from 2. The upper limit of m is constrained by the inequality k(m1 less than or equal to n, and approximating k as the smallest possible base, which is 2, we derive that m is bounded by log 2, n, plus 1. For a fixed m, finding k boils down to a binary search problem, where the range of k is from 2 to n(1/m1). These insights set the stage for designing an efficient algorithm to solve the problem. To implement the solution, we begin by parsing the input, converting n to an integer if it's provided as a string. Next, we iterate through possible values of m, starting from the largest, which is approximately log 2, n, and decreasing to 2. This order ensures that we prioritize longer sequences, which correspond to smaller values of the base k. For each m, we determine the range of possible bases k, starting at 2 and going up to n(1/m1). Within this range, we use binary search to efficiently identify a base k that satisfies the equation, k to the power of m1 divided by k1 equals n. During the binary search, we calculate the left-hand side of the equation for each candidate k and compare it to n. If a valid k is found, we update our result and stop further checks for smaller m values, since the sequence length is inversely related to the base size. Finally, after exiting the loop, we return the smallest base k that meets the conditions, ensuring optimality and correctness. The algorithm uses a few key data structures for efficiency. First, the input n is stored as an integer to enable fast arithmetic operations. For binary search, we maintain variables to track the low and high bounds of the search space, with low initialized to 2 and high calculated as n(1/m1) for the current m. A single result variable is used to store the smallest valid base k once identified. The core operations driving the algorithm include the geometric series formula, which allows us to test potential k values without explicitly summing terms. Binary search is the critical technique that reduces the search space for k from linear to logarithmic complexity for each value of m. To handle the large powers involved, Python's built-in POW function is employed for efficient exponentiation. Analyzing the overall complexity, the outer loop over m runs approximately log 2 n iterations. For each m, the binary search over k takes logarithmic time relative to n(1/m1). This results in a total complexity of roughly O log 2 n * log n, making the algorithm scalable even for large input values. When considering edge cases, the algorithm handles scenarios like the smallest n, which is 3, where the smallest base is 2 with m equal to 2. For prime numbers, the smallest base is often n1, such as 7 in base 6. Numbers that are powers of 2, like 8, usually have small bases, as they can be expressed compactly. For example, 8 equals 1 plus 2 plus 4 in base 2. For large n, the logarithmic bounds on both m and k ensure the algorithm remains efficient. To further optimize, we leverage mathematical bounds, avoiding iterative summation by using the geometric series formula. Breaking out of the loop early when a valid base is found reduces unnecessary computations. Additionally, Python's POW function ensures fast and precise calculations for large powers, which is vital for maintaining both speed and accuracy in the face of large inputs. These optimizations collectively make the approach robust and efficient across a wide range of input scenarios. This implementation solves the problem of finding the smallest good base for a given number n efficiently by leveraging properties of geometric series. Here's a detailed explanation of the code. 1. Input parsing * the input n, as a string, is converted to an integer for mathematical computations. Python. Number equals int, n. 2. Maximum possible sequence length, m. The maximum value of m is derived from the fact that for the smallest base k, k(m) must not exceed n. This maximum m is effectively log 2, n, because the smallest k greater than 1 is 2. The length of the binary representation minus the 0b prefix gives this value. Python. Max_m equals len, bin, number, 2. 3. Iterating over possible values of m** starting from the largest possible m down to 2, we test each sequence length. This ensures we find the smallest base k for the largest possible m. Larger m implies smaller k, so iterating in reverse guarantees the smallest base is found first. Python. For m in range, max_m, 1, minus 1. For estimating the base k * for a given m, the base k is estimated using the formula k is almost equal to n(1/m1). This is derived from the geometric series sum formula rearranged to isolate k. Python. K equals int, number, 1/m1. 5. Verification of the base * for the estimated base k. We check if it satisfies the geometric series sum formula for m terms equaling n. If true, k is the smallest good base, and we return it. Python. If km1 // k1 equals number, return str k. 6. Fallback to default base * if no valid base k is found for m equals 2, the smallest good base is n1, which corresponds to representing n in base 10 as 1 plus n1. Python. Return str, number 1. The time complexity of the solution is efficient due to the logarithmic search for m and the constant time arithmetic checks for each m, making it suitable for large values of n. The algorithm ensures correctness by iterating from the largest possible sequence length to the smallest, guaranteeing that the smallest base is found first. This is the Java implementation of the smallest good base problem, LeetCode number 483. The logic mirrors the Python solution, using a loop to test potential base values from the largest possible sequence length down to 2. The big integer class is used to handle large numbers and prevent overflow during calculations. The math.pow function estimates the base, and modular arithmetic checks if the base forms a valid sequence. The solution ensures precision and handles edge cases efficiently. The output is the smallest good base as a string. In this problem, we aim to find the smallest base k greater than 1 such that a given number n can be expressed as the sum of m consecutive powers of k. Mathematically, this means we need to express n in the form k to the power of m1 / k1 for some integer k in sequence length m. For example, if n equals 13, we start by converting it to an integer and calculating the maximum possible sequence length, max_m, which is determined by the binary representation of n. Here, the binary form of 13 is 1101, so max_m is 4, meaning we will test values of m from 4 down to 2. Next, we iterate over these possible values of m to check if a valid base k can satisfy the equation for n. Now, for the first example with n equals 13, we begin with m equals 4. Using the formula for k, we calculate it as int 13 caret 1 divided by open parenthesis 4 minus 1 close parenthesis, which gives k equals 2. Substituting this into the equation, we verify whether k to the power of m1 / k1 equals number. Here, 2 to the power of 4 1 / 2 to 1 equals 15, which does not equal 13, so we proceed to the next sequence length. For m equals 3, the computed base is k equals int 13 caret 1 divided by open parenthesis 3 minus 1 close parenthesis equals 3. Substituting k equals 3 into the equation, we find 3 cubed 1 / 3 to 1 equals 13, which matches our target n. Thus, we have found a valid base, k equals 3, and the output for this example is 3. In the second example, where n equals 4681, we again start by converting n to an integer and calculating max_m, which is derived from its binary representation. Here, max_m equals 13. For m equals 13, we compute the base k equals int 4681 caret 1 divided by open parenthesis 13 minus 1 close parenthesis equals 2. Substituting k equals 2 into the equation, we find 2 to the power of 13 1 / 2 to 1 equals 8191, which does not match 4681. Continuing this process for smaller m, we eventually test m equals 5 with k equals int 4681 caret 1 divided by open parenthesis 5 minus 1 close parenthesis equals 8. Substituting k equals 8, we calculate 8 to the power of 5 1 / 8 to 1 equals 4681, which satisfies the equation. Thus, the valid base for this example is k equals 8, and the output is 8. For the third example, where n equals 10 caret 18, we calculate max_m equals 60 based on the binary representation of n. Starting with the largest possible sequence length, m equals 60, we compute k equals int 10 to the power of 18 caret 1 / 59 equals 2. Substituting this value, the equation does not hold, so we reduce m and continue testing. After iterating over several values of m, we eventually find a valid base at m equals 2, where k equals 99999999999999999. This satisfies the equation, and therefore the output for this example is 999999999999999. In this problem, the time complexity is influenced primarily by the outer loop and the operations performed during each iteration. The outer loop explores potential sequence lengths, represented by m, starting from its maximum value, which is approximately log 2, number, and decreasing down to 2. As a result, the outer loop executes O, log, number, iterations. Within each iteration, two key operations dominate the runtime. First, the base estimation step calculates number raised to the power of 1/m1. This involves computing a fractional power, which can be performed in O, log, number, time using efficient numerical algorithms. Second, the sequence verification step evaluates whether the given base and sequence length produce the input number. This step includes calculating km, subtracting 1, and dividing by k1. The most computationally expensive part is km, which, when using modular exponentiation, takes O, log, m, asterisk log, k, time. Since k is at most number, this simplifies further to O, log, number, asterisk log, number. Combined, these operations contribute to the overall complexity of each iteration. When we assess the total time complexity, the outer loops O, log, number, iterations and the inner operations O, log, number, asterisk log, number, complexity combine. This results in an overall time complexity of O, log, number, asterisk log, number, asterisk log, number. Shifting to space complexity, the solution is very memory efficient because it does not rely on additional data structures. The primary contributors to memory usage are the input conversion and intermediate variables. The input string n is converted into an integer number, which requires O, log, number, bits to store. Beyond that, variables like max_m, m, and k are simple integers or floating point numbers, requiring constant space, or O, 1. Therefore, the overall space complexity is O, log, number, which stems from storing the input number. Let's now compare this optimized approach to a brute force solution. A naive method would involve testing all possible bases k, ranging from 2 to number 1, and verifying whether the sequence matches the input number. For each base, the verification process would involve iterating through up to log_k, number, terms. This results in a total time complexity of O, number *log_k, number, which is significantly less efficient than the logarithmic scaling achieved by the optimized approach. The optimized method, on the other hand, relies on the mathematical relationship between the base k, the sequence length m, and the input number. By narrowing down the range of possible sequence lengths and efficiently estimating potential bases, the algorithm avoids redundant computations and achieves an exponential improvement over the brute force approach. Finally, let's analyze the best, average, and worst case scenarios for this solution. In the best case, the smallest good base is found during the very first iteration of the loop. This typically occurs when the sequence length m is large, and the base verification succeeds right away. In such cases, the complexity is O, log, number, log, number. In the average case, the loop iterates over a subset of possible values for m, and the correct base is found after a few iterations. The complexity here remains O, log, number, log, number, log, number. In the worst case, the loop must exhaust all possible values of m, and no base is identified until the fallback case of number 1. Even in this scenario, the complexity does not change, it stays consistent at O, log, number, log, number, log, number. This uniform time complexity across cases highlights the efficiency and robustness of the optimized solution. When solving the smallest good base problem, there are several common mistakes to watch out for. One major mistake is using brute force to iterate through all possible bases from 2 to n1, checking if the number can be expressed as a sum of geometric progression terms. While this approach might seem straightforward, it leads to extremely poor performance, especially for large inputs up to 10 to the power of 18, as the time complexity becomes linear in n. Instead, we need logarithmic time complexity to handle such constraints effectively. Another common issue is ignoring the fundamental relationship between m, the length of the representation, and k, the base. The equation n equals the sum of a geometric progression, specifically, k to the power of m1, /k1, must hold for integer values of both k and m. Failing to identify this critical constraint leads to wasted computations and incorrect answers. Floating point arithmetic errors are another pitfall. When calculating k as n raised to the power of 1/m for large numbers, small inaccuracies in floating point precision can cause incorrect results. To mitigate this, always verify results using integer arithmetic rather than relying solely on floating point calculations. Finally, skipping edge cases, such as when n is a small prime number, can result in solutions that fail under certain conditions. For example, in these cases, the only valid base might be n1, and overlooking this can produce incorrect outputs. Now, let's delve into optimizing the search process and the insights that can simplify this problem further. One inefficiency arises when iterating through all potential values of m up to log 2, n, without refining the search space. Remember, the maximum value of m is constrained by log 2, n, because the base k must be at least 2. By focusing only on feasible values of m, we can eliminate unnecessary computations. A key insight for tackling this problem is to reframe it as finding integers k and m such that the sum of the geometric progression equals n. This perspective simplifies the problem significantly. Instead of testing every possible value of k, we can use binary search to efficiently determine k for a given m. This reduces the problem's complexity to O log n asterisk log n, a dramatic improvement over brute force. Another important consideration is recognizing m as the length of the representation. By iterating from the largest possible value of m, log 2, n, down to 2, we can ensure that we identify the smallest base first, which is the goal of the problem. To further optimize, pre-computing powers of numbers can speed up binary search operations by reducing repetitive calculations, especially when working within a constrained range. This problem also connects to several related problems that reinforce the concepts of number bases and representations. For example, LeetCode number 258, add digits, explores properties of numbers in different bases, while LeetCode number 400, nth digit, involves understanding number representations and arithmetic patterns. Similarly, LeetCode number 306, additive number, focuses on identifying sequences with specific numerical relationships, and LeetCode number 168, Excel sheet column title, deals with base conversions in a non-standard format. Exploring these problems can provide additional practice with related patterns and techniques. As for alternative approaches, one strategy is to iterate over m rather than k, starting from log 2, n, and working down to 2, we compute k for each m using binary search. This avoids redundant computations and ensures logarithmic scaling but requires careful handling of edge cases and the potential for integer overflow. Another method involves using mathematical approximations to estimate k for large m. While this can be faster, it introduces the risk of precision errors and demands thorough validation of the results. Finally, pre-computing values of the geometric progression formula for small ranges of k and m can speed up the computation. While less practical for very large numbers, this approach can be useful for smaller constraints where lookup tables are feasible. Thanks for sticking around. In this session, we explored the smallest good base problem, leveraging binary search and mathematical reasoning to derive an efficient solution. Remember the importance of combining algorithmic approaches with theoretical insights. If you enjoyed this walkthrough, please like, subscribe, and share with your peers. See you in the next problem-solving session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!